The interstitial space expands during vasodilation, opening channels that were sealed moments before. Blood vessels dilate, a threshold breached as nitric oxide signals relax smooth muscle fibers. But this dilation is just the beginning. What follows is a cascade of precision, where every step must align within microns and milliseconds. If these thresholds miss their mark, the system fails. Vessels remain dilated but vulnerable, unable to repair themselves. Instead of healing, they become sites of chronic inflammation, leading to tissue damage and disease. When everything aligns, something remarkable happens. Mesenchymal stem cells migrate to the site, guided by gradients of oxygen and growth factors. These MSCs don't just arrive, they decide the fate of the vessel. They activate genes in response to hypoxia, releasing growth factors that stimulate angiogenesis. New blood vessels forming from existing ones. This is not a random process, but a finely tuned mechanism, where each step is critical for survival. What decides whether this mechanism succeeds or fails? The answer lies in the thresholds that must be crossed and the precision of their alignment. Kuo et al. 2018. Thermal imaging reveals a critical shift in blood vessels. Blood flow increases when vessels dilate, measured in mAg. Imagine a garden hose that expands to let more water through. When the pressure reaches a certain point, the hose widens, allowing more fluid to flow. This is vasodilation. At this threshold, blood vessels act like adjustable pipes. Below it, they remain narrow. Above it, they expand to enhance circulation and regulate temperature. This expansion sets the stage for understanding how our body maintains its delicate balance. Next, we explore what triggers this critical shift. In Zhang et al. In vitro assay, researchers observed a critical phenomenon using advanced microscopy. Below a certain damage threshold, cells remain stationary, like cars stuck in traffic. Above it, they began to move at an astonishing rate, cells or hour. This rapid movement is the first step in self-repair. Imagine a pressure valve that only opens when the pressure reaches a specific point. This is what happens with mesenchymal stem cells. Below the threshold, they stay put. Above it, they spring into action, rushing to the site of damage. Wang et al. 2018. Flow cytometry study reveals a critical boundary in blood vessel repair. Below a certain threshold, damaged tissue remains starved of oxygen and nutrients. Above it, new vessels sprout like branches from a tree, expanding the network by square millimeter each week. This is the angiogenesis threshold, the point where growth factors trigger a cascade of cellular activity. Imagine a pressure valve that locks open when the pressure reaches a specific point. Below this threshold, nothing happens. Above it, the valve releases and the system responds. In blood vessels, this valve is the concentration of growth factors like VEGF. Once these factors reach 5 ng or ml, they unlock the cellular machinery that builds new pathways. Li et al. 2017 used a protein assay to measure VEGF concentration in damaged tissue. The results were striking. Below 5 ng or ml, the environment remains stagnant. Above this threshold, a chemical switch flips, unlocking a cascade of growth factors. This boundary is like a pressure valve. Sealed below it, bursts above it. VEGF, or vascular endothelial growth factor, is the key player here. When its concentration surges past 5 ng or ml, MSCs differentiate and promote healing. This threshold sets the stage for understanding how these growth factors coordinate to rebuild damaged blood vessels. Smith et al. 2020 clinical trial data reveal a stark failure state, a reduction in tissue repair among patients per year when hypoxia-inducible factor is inhibited. Below this threshold, the body's natural repair mechanisms falter. Imagine a pressure valve that fails to open when needed. The system remains sealed, unable to release the necessary resources for healing. This failure highlights the critical role of HIF in activating genes essential for tissue repair. When HIF fails to activate, the consequences are dire. Tissue repair is compromised, leading to chronic inflammation and degenerative diseases. The body's ability to respond to hypoxia and initiate the necessary gene activation is crucial for maintaining health. Without this precise mechanism, the system cannot heal itself effectively. The joint improbability of all 5 thresholds aligning, vasodilation, MSC migration, hypoxia-induced gene activation, growth factor release, and angiogenesis, reveals the intricate and finely tuned nature of the body's self-repairing mechanisms. Each step in this cascade is a threshold that must be crossed precisely for the next phase to begin. Consider the vasodilation switch again. When blood flow is disrupted, it opens to allow more space for repair cells to move in. The pressure valve analogy holds true here as well. Below the threshold, nothing happens. Above it, a cascade of events is set into motion. Consider the vasodilation switch. It opens when blood flow is disrupted, allowing more space for repair cells to move in. Next, mesenchymal stem cells migrate to the site of injury, guided by chemical signals. These cells are like construction workers arriving at a damaged building. Hypoxia-induced gene activation follows, where low oxygen levels trigger genes to produce proteins necessary for repair. It's as if the lack of air turns on a light, signaling the body to act. Growth factor release is the next step, with factors like VEGF reaching critical concentrations to unlock cellular machinery. Finally, angiogenesis occurs, forming new blood vessels that deliver essential nutrients and oxygen. The precision required for each threshold to align is staggering. Imagine a series of dominoes, where each must fall at the exact right moment for the chain reaction to continue. If one domino is out of place, the entire sequence fails. In the body, this coordination ensures that every step in the self-repair process happens exactly when needed. The beauty of this mechanism lies in its redundancy and robustness. Even if one pathway is compromised, others can often compensate, ensuring the system remains functional. This resilience is a testament to the body's ability to adapt and heal itself under varying conditions. Understanding these thresholds provides a deeper appreciation for the complexity of biological systems and the precision required for self-repair. How does this intricate coordination challenge our understanding of biological processes? The more we learn, the more we realize how finely tuned each step must be to ensure the body's ability to heal. In the next episode, delve into the role of immune cells in tissue repair and explore their interaction with these self-repairing mechanisms.